All right, hello everyone. Welcome to lesson 11. So on the previous lessons, we began talking about what a derivative is and how they can be represented as functions. Now, in the previous lessons, the way we saw derivatives, we saw them as limits. So, for example, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And in practice, when we wanted to compute f prime of x, which tells us about the instantaneous rate of change of our function, we usually had to do a bunch of algebra. So we substituted in x plus h and x into our function, and we can't plug in h right away because of this h in the denominator, so we would be dividing by 0, which is a problem. So first we needed to do a bunch of algebra first. And as you've seen through some examples and likely the homework as well, this can be kind of tedious for all but the most simple functions. So what we're going to begin doing now is we're going to begin learning alternative ways of computing the derivative without having to rely directly on this limit definition right here. And we're going to begin that today by talking about how to find the derivative of power and exponential functions. All right, so let's get right into it here. Let's say that we have a function f of x, and this is x raised to the nth power, where n is some constant value. Now, n could be a whole number, or it could be a fraction, or it could even be something irrational like pi. It could be negative as well. N could be any real number we want here. So if f of x is x to the n, then it turns out that f prime of x will be n times x to the n minus 1. So what we effectively did here was we took this power, this original power n, we moved it to the front of our x, so we bring the n down here to the front, we multiply it, and then we lower the power by 1. And that's it. That's all we have to do to find our derivative. So for example, let's go ahead and look at some basic examples here. Let's say we had f of x being x cubed. So if we want to find f prime of x, or the derivative of this function, what we do is we bring the old power to the front and multiply. So we have 3. And then we lower the power by 1 to get our new power. So we have 3x squared. And that's it. That's all we have to do. Now you may remember, I don't know if we've done x cubed specifically before, but in order to do it the old way, or by the limits here, we would have had to have x plus h quantity cubed, and then minus x cubed. So we would have had to cube out x plus h, which might take a little bit, and then we would have to simplify and then cross out our h's and then evaluate the limit. So no matter what, this is way faster to do it this way rather than using the limit definition of the derivative. Let's take a look at a few more examples. So let's say that x has a power that is not just a whole number. Let's say it's x to the 1/2. The rule works exactly the same way. If we want to find the derivative of this function, x to the 1/2, aka square root of x, then what we do is we bring the power down to the front. So we have 1/2 right there, and then we have x, and then we lower the power by 1. Now the thing is if we subtract 1 from 1/2, we end up getting negative 1/2. We subtract 1 no matter what, even if it would make the power be negative. And another way of writing this, since negative powers can go on the bottom, would be like that, or if you prefer the square root notation, we could write it like this as well. So all three of these answers are completely acceptable, and we get them using what's called the power rule. That's the name of this technique. All right, let's take a look at one more example. Let's say f of x is 1 over x squared. All right, now you might think, okay, well, if I do the derivative, I can just bring this 2 to the front of this x and then lower the power by 1, so we get 1 over 2 times x. But the thing is that this rule only works if it's x to a power, not 1 over x to a power. But the good news is that we can write this in a different way. We can write this as x to the negative 2. then we can go ahead and use our power rule here. So f prime of x, we bring this negative 2 to the front, and then we have x, and then we lower this by 1. Now this is a really easy place to make a mistake, since you see the 2 here, like, okay, I'll lower it by 1, so then I have negative 1. But remember, we're doing negative 2 minus 1. So it's actually going to be negative 3. So be careful for this. This is a really easy mistake to make right here. And then if you'd like, we could get rid of the negative exponent and write this in the denominator here. So it's negative 2 over x cubed. So in a nutshell, doing the derivative of x to a power is really easy. We just bring the old power to the front and then lower the power by 1. That's literally it. That's all we have to do here. All right, now I want to talk about some other rules before we move on to derivatives of exponential functions. So let's talk about the sum or difference of functions. So let's say that we want to take the derivative of two functions, and they're either added or subtracted together. It doesn't really matter which. Then what we can do is we can do the derivative of each one of them separately. So for example, I can apply the derivative to f of x and make f prime of x. We keep whatever the sign is, so if it was positive here, it'll be positive here, and same with negatives. And then we could do the derivative of g of x. So in summary, if we have the sum or difference of functions, we can simply take the derivative of each one of them separately. So derivatives split over addition and subtraction. One important note, which I'm going to star, is that the derivative of f of x times g of x, and you could also say f of x divided by g of x, is not equal to f prime of x times g prime of x right here. So I want you guys to note this right here. So this works for addition and subtraction, but if you got multiplication, or we could also stick division here as well, that's not going to be true. We're going to learn a special way with dealing with two functions multiplied together in the future, but for now we can't do that. We can just only deal with addition and subtraction. However, one type of multiplication that actually is okay is if we have the derivative of some constant times a function like this. So where c is a constant. Then what we could do is the derivative actually ignores the constant. So the constant moves out, and we could just do the derivative of our function. So we have c f prime of x right here. So this actually is something that's true. If there's just a number in front of your function, you can ignore it and just do the derivative of the function without the coefficient. Now why these rules work, it's because the same rules work on limits. Remember that the derivative is nothing more than this limit right here. And if you have two limits added together and they both exist, then you can do each limit separately. And if you ever have a constant inside your limit, you could always move the constant outside of the limit and do the limit without the constant. So these rules right here come from the limit definition of the derivative. And if we wanted to prove these rules, then we would use the limit definition of the derivative up here. So that's one thing it is definitely good for, is proving facts about derivatives is this form. But for practical purposes, we usually use one of these rules to do a derivative. Okay, so let me give you an example or two of these, using these rules. Let's see here. Let's suppose that our function is 3x squared plus 9x to the negative 1/2. And our goal is to find f prime of x. All right, so what would that be? Well, since there's an addition sign here, we could just do the derivative of this, so find the f prime for this part, and then we could do the derivative of this, find the derivative of the second part. So I'm just going to focus on doing the derivative here first. So I'm going to do the derivative of 3x squared, and then I'll worry about the 9x to the negative 1/2 afterwards. So I can do the derivative of each one separately. All right. So let's go ahead and do this here. So we can use this other rule right here, and we can move constants outside of our derivative. So the derivative doesn't really care about what's going on with these constants. So we can move the 3 out of this one, and to save time, I guess I'll just move the 9 out of this one over here. And then finally, we get to a point where we can use our power rule, which we learned up here. So remember, the way that works is we bring our power down to the front and then lower the power by 1. So this will be 3, and then I bring the 2 down, and it'll also be multiplied by this 3. And then I have x, and 1 lower than 2 will be 1. Or I could have just written x. That's fine too. All right, next I'm going to use the power rule on this as well. So I have 9, I multiply by the old power, negative 1/2, and then I lower the old power by 1. So negative 1/2 minus 1 will be negative 3/2 right here. And then if I'd like, I can actually multiply all of this out and clean things up a bit. So this will be 9/2 x to the negative 3/2. And there we go. Now once you get used to doing these rules, you won't need to write out all of these steps right here. In fact, eventually you'll probably just be able to start here, then immediately end right here. But it's good to be aware that these rules exist, at least for the time being. And then eventually they'll become so natural that you don't really think about them anymore, once you get enough practice doing this. All right, let's take a look at another example here. This one will be a bit different. So here's another example. Let's say that f of x is, well, why don't I use different notation to give you guys exposure to other notation. Well, let's say we have y is x squared plus x to the 4th plus 1 all divided by x cubed. Okay, so let's see if we can find out what y prime is going to be. Okay, now you may look at this and you'll be like, okay, well I know how to do the derivative of each of these. This will be 2x, this will be 4x to the 3rd power. And then as we saw in the previous video, the derivative of any constant will be 0. You can almost imagine it as being part of the power rule. You have something to the 0th power as a constant, and you can almost imagine you're bringing the 0 to the front, if you like. That's not, there's a little technicality about that, but that's kind of what's happening here. All right, but the thing is that we're dividing here. And another thing I said earlier is that derivatives don't work well with division. So we're going to have to come up with a way of dealing with that, but that's for a future lesson. So how are we supposed to deal with this dividing by x cubed? Well, what we do is we split up our fraction by dividing each one of these by x cubed before we do the derivative. So I have x squared over x cubed. That will simplify to be 1 over x. I have x to the 4th over x cubed, which will simplify to be x. And then I have 1 over x cubed, which is just 1 over x cubed. All right, now I'm ready to, well, actually, let me write it in the negative exponential form, and then I'm ready to use my power rule here. All right. And so remember, when we do the derivative of things added together, we just do the derivative of each piece that's being added separately. So now we're ready for y prime. Let's see, we're going to do the power rule here. So we bring down a negative 1, and then we have x to the negative 2. The derivative of x, well, technically it's x to the 1st power, so we bring down a 1, which doesn't do anything, and then we lower this to be 0, which is actually just anything to the 0th power will be 1. So the derivative of just x will be 1. And then here, we bring down our negative 3 to the front, and then we lower this power by 1 to be negative 4. Not negative 2, it's going to be negative 4 right here. And there we go, we found y prime. And then now we can maybe write it a little differently if we'd like, although this is a totally acceptable answer as well. And there we go. So there is our derivative right here. So for the time being, if we do see a fraction, see if there's a way to get rid of this division here before you do your derivative. All right, so there's that. Now, finally, the last thing I want to talk about is the derivative of exponential functions. So what's an exponential function? An exponential function is where we have some fixed number, let's call it b, and that's raised to the x power. So previously we had x raised to a constant n. Now we're having a constant, which we're calling b. B is a constant. And another thing we're assuming is that b is greater than 0 and that b is not equal to 1 right here. So anyways, that's what's going on. I guess we could use the case where b equals 1, but we're just going to skip that. So we have f of x is b to the x. So let's say we want to find out what the derivative of this is going to be right here. Well, before we do, so the reason why the derivative of this is the way it is because of our limit definition of the derivative. So I'm going to kind of give like an introduction to that, but there's a lot of details, so I'm not going to go over the whole thing. If you're interested, feel free to email me. I can give you the whole story. So f prime of x is f of x plus h minus f of x over h. So if I apply that to b to the x right here, and if you're uncomfortable thinking about this as a constant, you can kind of just put your favorite number in there if you'd like. So you can imagine this maybe is like 2 to the x, or e to the x, or pi to the x, or whatever you'd like, so long as it's positive and not 1. So if we do this, we have b, but instead of x, I'm going to put x plus h, well, after I do my limit. Then I have b to the x plus h minus b to the x divided by h. Now, using exponent rules, what I'm going to do is I'm going to factor out a b to the x from this. Because b to the x plus h is b to the x times b to the h, because addition in exponents is multiplying outside of the exponent. Alright, so my limit simplifies to this. Now notice that b to the x, it doesn't have any h's in it. And with limits, if you don't have the variable that's your limit is involving, you can move whatever that is outside. So we have b to the x, and then we have the limit as h goes to 0 of b to the h minus 1 over h right here. Alright, so then we have this kind of bizarre limit right here, and this is where things end up getting technical here. So I'm going to skip over those details, but of course you're welcome to ask me about those elsewhere. This is going to end up being natural log of b right here. And then we have this b to the x. So this b to the x is the same right here, and this number, this limit, ends up being natural log of b right here. So in summary, what is this saying? If f of x is b to the x, then that means that f prime of x is natural log of whatever b is times b to the x. So it's actually a very similar derivative. The derivative is very similar to the original function. You're just kind of tacking on something extra here. Now, probably the most common form we'll see this in is using the special number e. So let's say f of x is e to the x right here. Then using this formula right here, f prime of x is natural log of e times e to the x. But remember, natural log and e have a special relationship. Natural log asks, what number do I raise e to get the thing inside? So what number do I raise e to get e? Well, that's going to be 1. So since ln of e is equal to 1, we actually just get e to the x here. So that's pretty remarkable. It turns out that f of x is e to the x, and f prime of x is e to the x as well. So this is one of the few types of functions that's its own derivative. So effectively, if you take the derivative of this, it's not going to change at all, which is pretty remarkable. And one other thing I want to talk about before we see some examples here is what happens if we have e raised to a number times x, like this. What's going to happen then? Well, one way we can imagine this using exponent rules is this is like e to the a raised to the x power, where, as I said, a is constant. And a could be any value we like here. So this is equal to e to the a times x. Now what we're going to do is we're going to think of this like our b. So this is the number that we're raising to the x. We're raising e to the a to the x power. So if we pretend that this e to the a is just one single number b, then we can use this formula right here. So f prime of x, well, how do we use the formula? We have ln of whatever was raised to the x, so e to the a right here, and then we multiply by b to the x, so the original thing right here. Now ln of e to the a, kind of like how ln of e was 1, and you can almost imagine this as like e to the first power here. If you ever have ln of e to a power, that's going to simplify to be that power. So this was a right here. And then e to the a times x, if we use the exponent rules in reverse, we can rewrite this as e to the a times x. So the moral of the story here is that if you ever have e to a number times x, like maybe 2 or something, then you keep this the same, only you just stick whatever number that is in the front right here. So if f of x is e to the ax, then f prime of x, the only difference is we just stick this number in front. All right, so that's how we do derivatives of exponential functions. So I want to do maybe 2 examples of this. So my first example, find the equation of the tangent line to f of x equals 2e to the 3x plus 5x plus 1 at the point 0, 3. So remember, one of the ways that we imagined a derivative is as the slope of the tangent line. So we can use derivatives to help us find out what the equation of the tangent line is going to be. All right, so let's go ahead and find our derivative, because that will give us the slope of our tangent line. So f prime of x. Now, what we can do here is we can use all of the derivative rules that we've learned. So the first thing we're going to notice is that these are split up by addition here, right? You can almost imagine these 3 functions as like their own little islands separated by a sea of addition or subtraction. So our first function here, let's try to do the derivative of this. So the first thing we know, or the first thing about this that we notice is that derivatives ignore constants in front of them. So that 2 is just going to stay there, and then we're doing the derivative of e to the 3x. Now we just saw how to deal with this. If we ever have e to a number times x, the derivative will be the same thing, only we put a copy of that number up front. So I'm going to stick a copy of 3 up here, and then I have what I had before, e to the 3x. All right, so we've done the derivative of this part. Next we do the derivative of 5 times x. Now the derivative of any constant times x will just be whatever that constant is by the power rule. Because if you think about it, we have x to the first power, we bring that 1 down here so it doesn't change the constant, and then we lower this to be x to the 0, which we can consider to be 1. Finally, the derivative of 1 will be 0. So we've talked about this last time, the derivative of any constant function is 0. So we don't even need to write anything for that. So if we clean this up a bit, our derivative is 6e to the 3x plus 5. Now specifically, we wanted to find this tangent line at the point x equals 0 and y equals 3 right here. So let's see how we're going to do that. The x value in question here is 0, so we want to know what f prime of 0 is specifically. So this will be 6e to the 3 times 0 plus 5. Well, let's see. 3 times 0 is 0, and e to the 0, or anything to the 0 really, is 1. So we have 6 times 1 plus 5 makes 11 here. So this will be the slope for our tangent line. All right, so we have the slope for our tangent line, And remember that the tangent line has to go through this point right here. So we know a point on the line and the line's slope, so we have enough information to write the equation. So the equation of our tangent line is y minus y naught is m times x minus x naught, where x naught, y naught are going to be these values right here, the given values. So this means that y minus 3 is going to equal our slope, which we found to be 11, and then we multiply by x minus 0, or just x. So y is going to be 11x plus 3. And that's the equation of our tangent line. So if we were to draw the graph of this function, which probably looks something maybe like this, I'm not exactly sure, we would find that this would be our tangent line right there. All right, and then let's do one more example. Now this last example has to do with the similarity between our rules. So the only difference between our rules is that the power rule has to deal with x to a constant, and the exponential rules has to deal with a constant raised to a variable. So it can be easy to mix these up here. So I want to go over an example that puts our knowledge to the test. All right, so here's this function. We have f of x is going to be, let's see, so we're going to have e to the x plus 2 to the x plus x squared plus x to the e plus e squared plus 2 to the e. All right, so we're going to do the derivative of this. Now all of these are split up by addition, so that means that we do the derivative of each one of these terms separately. All right, let's take a look at the first one here. So this is an exponential function. We have e raised to a variable power. And as we saw earlier, e to the x is one of the few functions that is its own derivative. So the derivative of e to the x will simply be e to the x. Then we get to 2 to the x, which is similar to this right here. We're not going to lower the power and then bring down the x minus. We're not going to put the x here, lower the power by 1. This is a constant raised to a variable power. So the way we deal with that is we stick natural log of the base, so natural log of 2, and then we keep 2 to the x here. We technically did the same thing with e to the x, except that ln of e is 1, so we don't really need to write that. But remember, these are exponential functions. Now these next two are power functions, and they're power functions because our variable is the base now, and they have a fixed power. So the derivative of x squared, we bring the power down, and then lower the power by 1. So 2 goes to 1, and we could just leave that as 2x if we'd liked. And then we have x to the e right here. Now even though this is kind of a strange power, we can still do this exactly the same way that we did with x squared. Since it's a variable raised to a constant power, we bring the constant to the front, so we bring e to the front, and then we lower the power by 1. So we're going to have e minus 1 right here. All right, and then we have these final cases right here. So these ones can be a little bit tricky. So you might see this, we have e squared, and it's tempting to think, okay, we're going to bring the 2 down in front and then lower this power to be 1. Or maybe here we would put an ln of 2 out front and then we'd have 2 to the e, or something like that. But the thing is that e squared is just a particular constant value. E is 2.7 something squared, so that'll be a number, I don't know, maybe around 8 or so. But the point is that the derivative of a constant is 0, and this is just some bizarre constant. So the derivative of that's going to be 0. And then the same thing happens for this. This is 2 raised to the 2.7-ish power, which is a little bit less than 8, but it's still going to be some kind of constant. So the derivative of that will be 0. The moral of the story is if you don't see any x's in here and you're doing a derivative where the variable is x, then the derivatives of those will be 0. So even though they look like something we need to apply a rule to, these will just end up being 0. So these are kind of easy traps to fall into. The derivative of both of these will be 0. All right, so that's it for today's lesson. And when we pick up next time, we're going to learn about more of these derivative rules so we can find the derivatives of other types of functions as well. So I will see you all then.